All right, welcome to electrochemistry. This is part one of the electrochemistry series, and what we're going to do real quick, let me take away some of these things, is we're going to look at electrochemistry. So what is that? Electrochemistry is the idea of when chemical energy, energy within chemicals, changes into electrical energy. Very useful. We use it in a zillion different things. Batteries, how often do we use batteries in our daily life? All the time. Electrical energy has become sort of the mainstay for human comfort and existence, and so oftentimes there's an exchange of chemical to electrical energy. Our bodies do it. Our bodies do it to run our heart. Our brain communicates through electrical energy produced by chemical energy. So the applications are quite extensive, and understanding it is really, really important for understanding how things work. So what you need to do is to be able to figure out this process of chemical to electrical energy, you need to look at chemicals in terms of positives and negatives, or in terms of charges, you might say. Now, it's not the same as charges as you would have as you go down the periodic table, but that does apply. So in order to figure out the oxidation states of chemicals, you have to sort of follow these four rules. So I'll go over them real quick. Oxygen, you can almost be guaranteed it's going to be -2. The only times it's not is when it is a peroxide. I got hydrogen peroxide right here, and so you can see that H2, each one of these is going to be +1, and two of these is making that -1. So in peroxides, oxygen assumes a -1 oxidation state, but all the other times it's -2. So just look for those peroxides, and you could assume that every other time it's -2. Hydrogen, same thing, is always +1, except when it makes a hydride ion. So like sodium hydride right here, this will end up causing hydrogen to be a -1 instead of a +1, because sodium is a +1. Now, in general, you can use the oxidation numbers that are on the chart as charges. You can sort of do that, but some things have multiple oxidation states depending on the situation. So sometimes you have to analyze the situation to figure it out. Elemental form is also important to understand. So if it's an elemental form, like look, zinc right here has no charge. And if it has no charge associated with it, it's an elemental form, and therefore the oxidation state is 0. Our diatomics in elemental form, like hydrogen and oxygen, they assume doubles or diatomic states in elemental form. Nitrogen is another one. Hydrogen, oxygen, nitrogen, and all of group 7 then would have an oxidation of 0 if they're in elemental form by themselves. Now, when you put things into formulas, the overall charge of that formula is a sum of the individual charges. So let's get a little example going right here, and we'll show you how that works. All right, so in this case, we're going to analyze the sulfur ion. The first three are quite easy because we got oxygen. Remember, every single oxygen is -2. I got 4 of them, giving me a total of -8. So then I have 1 sulfur, and I have an overall -2 net result. So this one has to be +6, because +6 plus -8 gives me a -2 overall. So the oxidation state of sulfur here is +6. Let's look at this one. So I have 3 of these, so that's going to make me a -6 because each one is -2. We're going back to this rule 1 right here. And so I have an overall -2 charge. There's 2 of these, so each one of them must be +2, right? And these are totals because, really what I've done here is I've done -2 times 4, right? And here I did -2 times 3. So the oxidation state of oxygen is not -6. It's multiple of. But anyway, so +2 times 2 gives me a total of +4. When I combine that with -6, I get a net result of -2. So let's look at this right here. So the oxidation state of this one, just write this up here so we understand, is +4. This time is +6. Sulfur is one that has many different oxidation states. Now look at this guy right here. We have a total of -2 times 3, so we have a total of -6 for this. And so this is an overall -2, so this has to be a +4 as well. I just realized that I messed that up. It's a +2, right? +2 times 2 is +4, which is what we needed. Over here, this one's a little bit more complex, but when we look at the oxidation states that nitrogen normally assumes, it's in that group 5, so it normally assumes a -3. Carbon normally assumes a +4. So what does that make sulfur in this case? We've got an overall -1 charge. If I've got +4 and -3, this is going to have to be actually a -2. This one -2 in order to give me an overall -1 charge. So in the case of this right here, this molecule right here, we have an overall -2 charge. And I think that's thiosulfate, or thiocyanate, sorry. Thiocyanate is what that one's called. So anyway, so that's kind of a little bit of a breakdown on what to do as far as adding or giving oxidation numbers. And so let's look at an overall equation real quick, or just a couple of them, and kind of look at the different parts of these real fast. So, so what we have to do is we have to assign individual oxidation states to each of these. Well, we know that oxygen is going to be -2. There's 2 of these, so that makes my manganese here +4. Zinc is in elemental form, and so this one is 0. Hydrogen, we know hydrogen's always going to be +1. It's not a peroxide. And we know that oxygen is going to be -2, and that matches up. So what do we have over here? Hydroxide. Hydroxide is going to be, and let's see, well, let's go ahead and solve this in the sense of this just being an overall -1, because we know that the hydroxide ion is an overall -1. And then this is going to be -2 because it always is. And so these are all together right here. So what do we have to have? We have -1, -2. This is going to have to be +3 for this molecule to work out without having a charge overall, right? So now we have over here, we have the hydroxide ion. So those are going to be -1. And there's 2 of them. That makes zinc here a +2. All right, so now let's check out and see what changed. And that's kind of what you do. Once you assign all your oxidation numbers, you have to look at what changed. So let's look at manganese. Manganese went from +4 to +3, which means that an electron was added to it. When you add an electron to an atom, it's actually called reducing it. So manganese has been reduced. Which means that, that over here, it took, this particular atom on this side is responsible for taking an electron. So on the other side, the manganese would become the oxidizing agent. And so what we're saying there is it causes oxidation. So oxidation is the idea of getting rid of, so ridding yourself of electrons. So I'm going to put rid of electrons, right? And over here, reduction is gain in electrons. So that's kind of what we're looking for. So we see that manganese was reduced, which makes the manganese on the other side an oxidizing agent because it caused another element to get rid of an electron because it picked one up over here. So whatever's reduced on the other side is the oxidizing agent. So now let's look at our other things here. We have zinc, and we notice that zinc went from 0 to +2. So what happened there? Well, electrons were taken away from it. So zinc is oxidized because it lost electrons, which means that on this side, zinc is the reducing agent. Because of zinc, this one was reduced. And so this is the oxidizing agent because it gave electrons to this one. So see, there's 2 of them. It each lost 1. There's 1 of these. And so it all balances out. And we'll do some more balancing of equations, these particular equations, in a later video. But that sort of shows you one example. Let's do another real quick example, and let's just assign oxidation states. These ones are easy because N2 and O2, remember, are in elemental form. So the oxidation state of both of those is 0. But over here, it's not, because here we have +1. There's 3 of them. So that's going to give us a total of -3 for nitrogen. So nitrogen right here, -3 to cancel out the 3 positive ones on this side. So, so what happened? Well, nitrogen obviously went from a 0 to a -3. So electrons came into nitrogen. So it has been reduced. Remember, when you gain electrons, you're reduced. Which means if it was reduced, it means it's sort of opposite over here on the other side is the oxidizing agent. And then the opposite is going to be true for hydrogen. So hydrogen clearly was oxidized because it lost electrons. Oxidized, if it becomes positive, it loses electrons. That makes this the reducing agent. Oops, there we go. Forgot the A. There we are. Reducing agent. Sorry about the handwriting. So hopefully that kind of gives you a good idea about how to identify oxidation, reduction, reducing agent, and oxidizing agent.